Hello, today we're going to be doing 5.8, solving radical equations. This goes with our unit of 5.5 and 5.6. This is the last section in our unit, and in my opinion, I think this is, I don't want to call it easy, but I think it's easier than the other two sections. I think it's the most fun of the three sections that we've done. Hopefully you agree, but I know you guys always say I think some things are fun that you don't, but hopefully this section is okay. One thing I want to mention right off the bat is that I know in 5.6 I encouraged you to try not to use a calculator. Obviously I don't want you guys using calculators like as a crutch, but calculator is totally fine, and we're even going to go a little bit more into detail about how to use your calculator in this section. So if you have one, get it out and have it around you for this lesson. As always, you can pause or slow things down when you want to do some work. So we're going to start with a warm-up. So again, if you want to kind of pause these and give them a try before I do them, then do that now, but I am going to start doing this. So this first one, we actually haven't talked a ton about this, but I want to do it now. So this is adding two radical expressions. Now, you can add radical expressions, but when you're adding radical expressions, they have to be the same. It's kind of like they have to be like terms. So 27x and 12x are not like terms. So what we need to do here is we need to break these radicals down. Now that we have done before, all right? For a second, let's ignore the 2 and the 3 outside. So let's just focus on the radical 27x and the radical 12x. So if we have radical 27x, again, we're even going to ignore the x for a second. Let's break down this 27. So we have radical 9 and radical 3. And then we have radical 3 again. If you stopped at the radical 9, radical 3 and recognized that, that's fine. But we have these two 3's that are able to escape, so they come outside of our radical. Okay. Then we still do have 3 that is stuck inside. And we have this x that was stuck inside. So this radical 27 breaks down to 3 times radical 3x. Now, let's also bring our 2 back that was originally there. So we have 2 times 3 radical 3x, or 6 radical 3x. So that's the 27. Let's see what happens when we break down this 12x. So again, we're going to ignore the 3 for a second. We're going to break down the 12. Again, you can do it. I'll do with the x this time if you want to see. We have like radical 4 times radical 3 times radical x. Again, there's only an x there, so we can't do anything really with it. The 4 has a 2 and a 2 in it. So the 2 gets to escape. The radical 3 and x are still there. Now, we have to bring back the 3 that was here in the beginning. So we have 3 times 2x. So this becomes another 6 times radical 3x. Now, the outside number doesn't have to be the same for us to combine our like terms. In this case, they happen to be, which is great. But we have 6 radical 3x's, and we have another 6 radical 3x's. So what we have here is 12 radical 3x. I just wanted to talk about that because we hadn't really talked a ton about adding radical expressions. Adding radical expressions is not going to come up a ton in this lesson either, but I did want to talk about it and just kind of see how that looked. This next one, same thing. We're going to break this radical down. So again, I like to kind of separate them. So radical 72 and radical y to the 5th. So the 72, we've broken down numbers like this before. You could do 9 and 8. You could do 36 and 2. I think we've seen 72 a bunch of times. So we're going to break this down all the way to its prime factors. Then the 3's are going to escape. The 2's are going to escape. So that's 3 times 2 radical 2 because of that lonely radical 2. Then that gives us a 6 radical 2. Now with the y, if you think back to what we did last lesson, and this is important for us to remember, we can think about this as a power over root situation. So you can say y to the 5 over 2 power. Remember, when there's nothing here, that's an imaginary 2. Okay. Now, 5 over 2 does not come out evenly when you divide, but you can also think about it like this. We have 5 y's in here, and we're finding groups of 2. So there's a group of 2. There's another group of 2. So that means 2 y's get to come out, and 1 has to stay in. If you divide this, 5 divided by 2, you would get 2 with a remainder of 1. So that's this. So when we put these two things together, we have, let's change the color here. We have the 6 on the outside, the y squared on the outside, and the 2 inside, and the y inside. So we have 6y squared times radical 2y. Now this stuff is kind of left over from 5.6. So if you're looking at this being like, hey, you said this was going to be easier, and I don't think this is easier. Again, this is kind of remnants from 5.6, but we are going to have a test that includes 5.6. So I just didn't want you guys to forget this. So that is that. Let's see, my answers are going to come up here, but all my work is covering it. But this is the same answers that I had there. 12 times radical 3x, and then we had 6y squared radical 2y. Okay, now the next part of the warm-up, especially number 3. Number 3 is super key to what we're doing today. It is one of the most simple things on this warm-up, but it is maybe the most important problem in our warm-up. So what we have here is the cube root of x plus 2 cubed. Okay, so what you may notice here is that we have a 3 as our index, and we have a 3 as our power. So if you use the power over root rule, you're going to get something like x plus 2 to the 3 over 3, which simplifies to x plus 2 to the first power, because 3 divided by 3 is 1, or just x plus 2. Now, the key to realize here is that whenever you have a power and a root that are the same, they're basically going to cancel each other out. And the reason being is because we're dividing our power over root, and that's always going to be 1 if they're the same. So in a lot of our problems that we're doing in 5.8, our goal is going to be to get the radical to cancel. So we're going to be using this property where the index and the power being the same is super important. So I want you to remember that and keep that in mind. We'll discuss it many more times as we go through this. This one is more similar to the warm-ups we did on the slide before. What I would do here, there's a few ways you could handle this problem, but I would multiply 2 times 48y and get 96y. Or you could break down the 48 and bring the 2 back. I think this is less confusing this way. So again, you can break this down. It will include the y in our breakdown. Again, you are free to use a calculator in this section. You could do something like, let's see, 96. I mean, obviously you could use 2 and 48 because we just multiplied them together to get that. Then you could break down 48 again. So you could have broken down the 48 to start with and then kind of brought the 2 back, but when I do things like that, I usually forget that too, so I want to keep it in here. So we're just breaking these down into the prime factors. Don't have that much room here. So let's see what we have at the bottom here. I see a pair of 2's. I see another pair of 2's. And then I see a lonely 2 and a lonely 3. So we had one pair of 2's. We had another pair of 2's. We had a lonely 2, a lonely 3, and we had a lonely y. So again, 2 times 2, 4, 2 times 3 is 6y. So that is your answer to that. 4 times radical 6y. Okay, these bottom two are just asking us to write these in radical form. So this is just asking us to remember our power over root rule, okay? So whenever you see a 1/2 power, I want you to always associate that with a square root, okay? So I want you to associate that with a square root, 1/2 power, or if it's 1/3 power, we're talking cube root. Whenever there's a 1 up here, you're just talking about this being the root. So, for instance, x plus 6, and again, you can put the 2 there, or you don't have to, because whenever you don't have anything there, it's assumed to be a 2. Now this one, actually, let me go back to number 5 for a second. This one, these parentheses, I put them there. You don't need them there. If you write the square root of x plus 6, that's fine, because it's understood that everything under the square root is being square rooted. That's what's going on. But I want to show you something with parentheses in number 6. Here again we have power over root, so we're going to make our radical sign. Our root, the 5, is going to go right here, the 5th index, or 5th root. Now this one we have to keep the parentheses here. And the reason for that is because our power is going here. We have to make sure that third power is being applied to this whole thing. This would not just be 4 cubed or 3y cubed. It would be 3y plus 4 times 3y plus 4 times 3y plus 4. So we need to make sure that that whole thing is being cubed. In number 5, it didn't matter as much because it was just a first power. So you could kind of take or leave the parentheses, but if you want to always be safe, I would, if something's in parentheses, leave them in there to make sure. Again, I have the answers here, but my work is covering them all up. But these are the answers. Okay, so power over root is one super important thing to remember. And also remember that whenever you have a power and a root that are the same, they're going to cancel each other out. So those are the two key things to remember. Okay, so what we're going to do here in this section is we're going to solve radical equations. Okay, so radical equations are any equations that have a variable underneath a radical sign. So it could be a square root of x, could be a square root of x plus 2, could be, you know, cube root of x plus 17. As long as a variable is inside the radical and you have an equation, an equal sign, then you're dealing with a radical equation. Okay, so if you remember, we've done a lot of problems where we've had something maybe like x squared equals 4. And the way we went about solving that was by square rooting both sides. Now we did that because a square root and a squared cancel each other out. So that thing that we just talked about in the warm-up is something that we already kind of knew. So this goes both ways. If you have something squared and you want to get rid of it, you're going to square root it. If you have something being square rooted, you're going to square it, because these are inverse operations, okay? So the directions for solving radical equations are fairly simple. The first one, and this is something that a lot of people always forget, okay? You have to first get your radical alone. So whatever thing is inside the radical, that whole term should be alone with everything else on the other side. Then you can use these rules that we just learned, where a radical or a power and a root can cancel each other out, to simplify, and then you solve it, okay? So for instance, let's do this problem that's right here. I'm going to write it let me give myself a little bit more room. Okay, let's erase this. I'll do it up here. Okay, so this says the cube root, that's still an eraser. Okay, so this says the cube root of x minus 2 equals 0. So our first step says get the radical alone. So I want you to think about what that would mean, what we need to move to get our radical alone, okay? So hopefully you've thought of that. We're going to add 2 to both sides. Okay, that gives us the cube root of x equals 2. Now again, to get a cube root to disappear, again, our goal is to get x alone. we need to cube both sides. So we're going to cube both sides. Again, when you do that, all this cancels. You're just left with x, and then 2 cubed is 8. And that is your answer. Okay, so first get the radical alone. So if something's being added to it, you got to subtract it. If something's being multiplied, you got to divide. Just like you get any x term alone. Then use your power to get rid of it, and then continue solving, okay? So, one thing is that we have to be aware of extraneous solutions, especially when we're dealing with even powers. So when we're squaring things, raising things to a fourth power, we're going to be dealing with extraneous solutions, okay? So that means all your math might be right, but one or more of your answers might not work. So we are going to be making sure to check our answers here. Again, it doesn't matter as much when we're dealing with cubes or cube roots or fifth roots when they're odd. When they're even, we definitely want to check. And there's a couple of other situations that make it even more important to check, and I will get to those soon, okay? So again, just the first few, we're just going to check all of them just to make sure we understand how to check. And then as we move through the lesson, I'll tell you when it's super important, which ones are most dangerous, and you really need to check. So, as always, as we're going through these, before I do them, you might want to pause, or maybe you've already tried it you're on your own earlier. So if you haven't done this problem already, pause it, try it, and I'm going to show you how to do it right now. So we have 5 plus the square root of x plus 1 equals 16. So here's our radical term. We want to get that radical term alone. So we're going to say minus 5 from both sides. Okay? So then we're going to get square root of x plus 1 equals 16 minus 5, which is 11. Then we're going to square both sides. Now, the whole point of squaring both sides here is to get rid of this radical. Some people think that they need to bring this 2 in and put it on the x and make that x squared or something. You do not want to do that here. If you have a radical and an exponent, they're going to cancel each other out. So it's basically just like that leaves, and we're left with x plus 1. Again, the whole reason for that is because you're really doing x plus 1 to the power over root 2 over 2 power. So that just gives us x plus 1. I'll just write over it. Okay, so x plus 1 equals 121. Okay, now we're subtracting 1 from both sides. This just becomes a regular linear equation that we've solved a million times. So your x is 120. Okay, so now to check that, you're just going to put 120 back into your original equation. So at the very beginning, first one that we started with, you don't want to plug it back in here or something. You want to plug it back into your original. Okay, so 120 plus 1 equals 16. We're asking, do these two things equal each other? So 5 plus the square root of 121, does that equal 16? Square root of 121 is 11. Does 5 plus 11 equal 16? 16 does equal, I don't know why I wrote a check there. 16 equals 16. Yes. Okay, so this does work. Our answer is 120. Okay. So again, you might even, depending on where you are at, you might be able to kind of plug that in your head real quick and do it, but you can be sure that you did this problem right if you just do that check real quick. Okay. Now we have a cube root problem. So in case you are, I know the font sometimes is a little weird. This says 7 times the cube root of 5x minus 7. This is not 7 to the third power. The 3 is part of that radical. Okay? So again, if you haven't done it, pause and do it. Okay. So this time we have a 7 times our radical term. So to get rid of that 7, we're going to divide both sides by 84. Okay? So we're going to divide both sides. We have the cube root of 5x minus 7 equals 12. 84 divided by 7. Now, what we're going to do here is we're going to cube both sides. Okay, so we're going to, again, cube root and cube cancel. we're left with 5x minus 7 equals 12 cubed. Now that's an interesting thing. I know a lot of you guys are going to take your calculators out right now and you're going to do 12 times 12 times 12 because that's what 12 cubed means. But I want you to start to get more efficient with your calculator, so I'm going to show you real quick. So I'm going to leave this for a second. Oops, spoiler alert. Okay. I want to show you how to use your calculator more efficiently instead of doing 12 times 12 times 12. So what you have here, depending on which kind of calculator you have, you can raise things to powers using this button if you're on this EOC calculator, or using this button. Again, some of you might have other models of calculators, but if you don't have one of these two, I want you to kind of play around with your calculator and try to find a button similar to this. So what you're going to do, if you have this EOC calculator, to do 12 to the third power, you're going to do 12. You actually have a couple options here. You're going to do 12, obviously. Now, if you look right above the 1, there is an x cubed button. It says right there. So you could do 12, press the second button, and then press the 1 again. That gets you the cubed function. But if you want to raise it to any power, so the 4th power, 5th power, 6th power, whatever, you do 12 again, or whatever number you're raising the power to. Then this yx button, and then the power. So you do 12 yx 3, that will get you 12 to the third power. If you're on this TI-30XS calculator, again, you're going to press 12, then you're going to press this button. It's called a caret. It's also like on your computer how, if we're typing, that's also how we show a power sometimes. So 12, press this, and then the 3. So 12 caret 3, and then enter will get you your 12 to the third power. Again, you could do 12 times 12 times 12, but let's try to get more efficient with what we're doing, okay? So we're back here. Our answer's already up there, but okay, so we have 5x minus 7 equals 12 to the third power, which if you do that in your calculator, you get 1728. Okay, now you're going to add 7 to both sides. You get 5x equals 1735 divided by 5. And you get x equals 347. Okay? So, I'm seeing 347. I'm like, oh my gosh, we don't usually get numbers that are that high as our answers. That's weird. Usually my answer is like 5 or 7. So let's check it. So we got 7 times the cube root of 5 times 347 minus 7 equals 84. Okay, does it equal 84? Okay, so let's leave this for now. Let's 5 times 347 minus 7. I already did that. It's 1735 minus 7, or 1728. Okay, so does that equal 84? So what we need to find now is how do we do the cube root of 1728? Let's go back to our calculator slide here. Okay, so in our calculator slide, let's erase this ink here for a second. When we're looking to find a cube root of something, so not something cubed, but the cube root of something, you have, again, a couple of choices. On this, I'm not quite as familiar with this calculator because I have this one on the right. So I'm not sure about the order you're going to press these buttons. So you might, again, have to play around with that. But I believe, let's write down our problem here. We're trying to find the cube root of 1728, right? Okay. So I believe on this TI-30XA calculator, the EOC one, you are going to press the number first. So you're going to press like 1728. And then again, you have a choice here. If you look right above the 0 key, it says the cube root of x. So you press 1728, then you press second, and then you press the 0 key. I'm pretty sure that's the order that you're going in here first. But again, I'm not as familiar with this calculator, and I don't have one to test it. But I believe your number, you press 1728, whatever number is inside your radical, second, and then this cube root button. Or maybe you have a fourth root or fifth root or sixth root. You could also use this shift key up here where it says the xth root of y. So again, you could press 1728, second, this button, and then put a 3. Or I forget the order. That's the thing I'm not sure with this calculator. You might put the 3 in first. Test it. Again, these are the kind of things you should play around with before you have a quiz or a test. You want to get 12 out of here. Your goal is to get 12 as your answer. So you might want to play around with your calculator to figure that out. Now this calculator I'm a little bit more familiar with, so I can tell you on the right. You want to put your index in first on this calculator. So if you're doing like the cube root, the third root, you want to press the 3 first, then you want to press second, then you want to press this button again. Above the caret, you have that like xth root of whatever. So that'll show you the cube root of whatever, and then you put in your 1728. Again, make sure that you're pressing these buttons and you're getting 12 is your goal here, okay? So we'll go back here. So we did that. Hopefully we got 12 here. Then times 7 equals 84, and that does work. So that answer works. Okay. So again, it's 347. Here's your calculator stuff. All right, so just again, try these problems. Pause and do it, but I'm just going to go through them pretty quick here. Okay, because this one's similar to the one we did first. So we're going to subtract 4 from both sides. That leaves us with radical x minus 1 equals 1. When we square both sides, we get just x minus 1, because these cancel, the radical and the squared. Now, this is like a hopefully very easy. 1 squared is 1. That's a place where I see a lot of silly mistakes. If people are rushing, they might say like, oh, I see a 1 and a 2, that's 2, or something like that. So be extremely careful, because this problem should be easy, but if you're rushing, then we're going to add 1 to both sides. This is another place where I see silly mistakes, is people are too lazy to show this step right here, and so they end up like saying 1 minus 1 is 0 or something like that, but your answer here should be x minus 2. Okay, and again, if we plug this back in, we're going to plug 2 in as our x. So we have 2 minus 1 is 1. Oops, I forgot my plus sign. So 4 plus square root of 1. Square root of 1 is 1, because 1 times 1 is 1. And 4 plus 1 does indeed equal 5. So x minus 2 is our correct answer. Okay? All right. So again, this one, our radical is already by itself. There's nothing else going on. So we're just going to start right away. Again, we have a 3 here as our index, so we're going to cube both sides. Okay? So this gives us 3x minus 4 equals 2 cubed, which is 8. Again, a lot of room for silly mistakes here. Is like people sometimes cube the left side and then forget to cube the right side, so they'll end up with like 3x minus 4 equals 2, but you got to make sure you're cubing both sides. So now we're going to add 4 to both sides. 3x equals 12 divided by 3, x equals 4. Okay? So x does equal 4. If you check that, it does come out right. Again, you don't have to be as concerned with checking if it's an odd power, like a cubed. But if you want to like turn in a quiz or turn in a test and be like 100% sure that you're right, then checking is the way to do that. Okay? Okay. So example 5, this is our last, I'll say quote unquote easy one, and then we'll move on to some harder stuff. Okay, so we have 6 times square root of x plus 10 equals 42. We're going to start by dividing both sides by 6. That leaves us with square root of x plus 10 equals 7. We have a square root, so we're going to square both sides. That leaves us with x plus 10 equals 49. We're going to subtract 10 from both sides. And x equals 39 again. I know I'm going kind of fast on these, but you should always be pausing where you need to, and even pausing before I start and trying it on your own. So then hopefully when you're watching me, you're just kind of verifying stuff that you've already done. And again, you can check this. You can write out a check. You can kind of in your head check it. If I'm like, okay, if I put a 49 here, 49 plus 10, okay, that's, or sorry, I'm putting a 39 here, not a 49. 39 plus 10 equals 49, okay. Square root of 49, that's 7. 6 times 7 is 42. Okay, that works. So again, for some of you, it might be better to write everything out. For others of you, you might be able to do that in your head. So, okay, so x is 39. We're correct. All right, now here's where it gets interesting. In this one, we have two radical expressions. We have one on the left side, and we have one on the right side. One of them has a 3 being multiplied by it. The other one is by itself. Now, we said that the first thing you have to do here is get the radical alone. Now, it's impossible for us to get both of these radicals alone. Like, if I'm like, oh, I have a 3 here, so I should divide by 3. But then, if I divide by 3, now this radical is not alone. So, it's impossible for us to get both radicals alone. It's only possible for us to get one alone. So we have a radical alone right here. So we're fine. We're fine to start canceling radicals. So what we're going to do to cancel the radical is we're going to square both sides. Okay, so this side is squared. When we're squaring this right side, you have to make sure you square everything, not just the radical part. So we're squaring the 3x minus 2 in the radical. We're also going to be squaring that 3 that's on the outside. Okay, so this, the whole point was canceling it out, so we're just at 7x plus 2. On the right side here, this squared has to, you have to make sure you distribute it. So again, we're going both to that 3. So this 3 squared times, and then this part, the radical and the 2 cancel. So we're here. So the 3 had to get a radical on, or sorry, a squared on it, and then our radical and the squared canceled each other out. So that leaves us with 7x plus 2 equals 3 squared. That's 9 times 3x minus 2. That's in parentheses. We have to make sure this 9 gets distributed as well. So that gives us 27x minus 18. And our left side is still the same. Okay, so now this is just a regular linear equation. We want to get all of our numbers to one side, all of our x's to the other side. So I see a big amount of x's here, so I'm going to move my x's to the right side. Okay, so they stay positive. So we get 2 equals 20x minus 18. Then I'm going to move that 18. So 2 plus 18 is 20. Equals 20x. I want to get that x by itself, so I'm going to divide both sides by 20. 20 divided by 20 is 1. Okay, so we did all that work just to get an x equals 1. And again, you can plug that back in. This is a situation where I would probably plug it back in whenever you have, I'll tell you a few things to be kind of careful of when you're trying to decide, do I really need to plug this in and check it? I would say, if you have two radical terms, good to check. If you have stuff that's coming out negative, I'll show you an example of that in a minute. That's definitely a sign that you should check. And if you have any quadratic stuff that comes up, I would definitely check. So this one has 2 radicals, so I definitely think we should check them to make sure they both come out fine. So again, we're plugging 1 in to both of our x's. So we have, does this equal, 3 times 3 times 1 minus 2. Okay, so 7 times 1 is 7 plus 2 is 9. And then we have 3 times 1 is 3 minus 2 is 1. So the square root of 9 is 3. The square root of 1 is 1. So does 3 equal 3 times 1? Yes, it does. So our answer was indeed x equals 1. That works. Okay. So example 7. Again, we're in a 2 radical situation. So one of them is alone. So this one on the left side is alone. So that means we're ready to square both sides. So if we square the left side, we end up with 8x plus 6. And if we square the right side, again, make sure that 2 goes there. So 3 squared is 9. And then just x. Okay? So this is a nice one. All we have to do here is say subtract 8x, subtract 8x. We are left with 6 equals x, or x equals 6. Again, you're always allowed to switch the order of those things on different sides of the equal sign, so you can write x equals 6. Now, I want to show you what happens when we plug this one in. This one's interesting. Bring back some memories. So this one says if we plug in x, or 6 for x, we have 8 times 6 plus 6 equals 3 times the square root of 6. Now, we can't do the square root of 6, so this right side is looking kind of funky here, but let's see what happens here. So we have 48 is 8 times 6 plus 6. So we have the square root of 54. And we want to know, does that equal 3 radical 6? If we break down 54, we get 9 times 6, 3 times 3. We have a pair. They're allowed to escape. So 3 radical 6 does indeed equal 3 radical 6. So even though those didn't come out to nice, pretty numbers, the two sides of our equation were equivalent. So that's good. Okay. All right. Next problem again. We have 2 radical terms, but one of them is alone, one of them isn't. We have cubes, so we're going to cube both sides. Okay, so again, here we have a cubed, or a cube root and a cube. So that's just going to leave us with x plus 6, no longer inside the radical. Then here we got to make sure that 3 gets to that 2. So we have 2 cubed. And then this 3 and our index are going to cancel out. So we're just left with x minus 1. Okay. So now we have x plus 6 equals 8 times x minus 1. We're going to distribute that 8. So we get 8x minus 8. Again, we're now just a linear equation. We're getting our x's alone. So we get subtract x from both sides. So 6 equals 7x minus 8. Adding 8 to both sides. 14 equals 7x. And x equals 2. Now this one I did already check for you guys. Also, it's a cube, so we don't have to be as worried. But again, if you check it, it can help you avoid silly mistakes. Now, it can't, if it's something with an extraneous solution, that's where we got to worry about our even powers. But I'm not saying every time you do an odd power one, you're going to get it right. But it's less likely that something extraneous is going to happen. So I already did check it for you. It works. If you want to check it, obviously go ahead. Okay. Now, here's where we have, I can tell the situation is going to be dangerous here. I see a negative. I see a negative. I see an x that's outside the radical and an x that's inside the radical. Lots of crazy stuff going on. So I know, even before I start this problem, that when I finish this problem, I'm going to check this because so much stuff is going on here. You're going to see something else interesting that happens. So this is definitely one that whenever I finish, I know that I want to check. So let me erase those crazy arrows everywhere. Okay, now we have a radical expression, a radical term on the left side. It is alone. So that means we are ready to square both sides. So we're going to square both sides here. So again, over here, our radical and our exponent are the same. So that just leaves us with the negative 3x plus 33 escaped out of the radical. Now, I want you to think for a second before I spoil, what is that right side going to look like? Okay, so think for a second, but now I'll tell you. Again, pause if you want to figure it out on your own. A lot of people's gut reaction is to just square the 5 and square the x. But remember, what this really means is 5 minus x times 5 minus x, okay? For those of you who have a good memory of perfect square trinomials or squaring binomials, you might be able to do this kind of in your head and figure out what's going on. But I will show you the whole distribution process just in case. So we have a 5 times 5. That gives us 25. We're kind of foiling here. I mean, we are foiling here. 5 times negative x is negative 5x. We have another negative x times 5, so that's another negative 5x. And then we have a negative x times a negative x. That's a positive, and it is x squared. Now, if we want to put this in standard form, the x squared is going to go first. The negative 5x and negative 5x are like terms. They go together. Okay, and then we end up with that. So that is the right side of our equation. One of your favorite things is going to come up here soon. Now, this is not a linear equation. This is a quadratic equation. When it's quadratic, we are no longer want to get our x's on one side and our numbers on the other. When it's quadratic, we want everything to the same side, make it equal 0. So here's our x squared. It's positive. We like that our x squared is positive. So we want to move this stuff from the left side to the right. Okay, let me just put that in its own space. Okay, so we're going to take this 3x and this 33, and we're going to move them by using their opposite signs. We're going to put them with their like terms. So the 3x goes with the 10x. Okay. All right. So we have 0 left on the left side, and then we have x squared. We have negative 10x plus 3x, so that gives us negative 7x. And then 25 minus 33 gives us negative 8. Now, everyone's favorite thing is factoring, okay? So we're going to factor this, and then we're going to use that factoring to solve. So we're going to leave 0 equals, we need two numbers that multiply to be negative 8, add to be negative 7. So we're going to have x minus 8, x plus 1, okay? So negative 8 times 1 equals negative 8. Negative 8 plus 1 equals negative 7. Now again, to solve this, we're going to say x minus 8 equals 0 and x plus 1 equals 0. Okay, now to solve that, we're going to add 8 to both sides. So we're going to get x equals 8. Again, I know some of you guys maybe don't need to show that step, but do what works for you. Okay, so we got these two answers. Now, we said at the beginning, we are going to have to check this because this had a lot of kind of red flags. We had a couple of x's, one on each side. We had some negatives going on. So, and we had an even power. So all that leads to, we definitely want to check this. So first thing we're going to check is the 8. So let's plug in 8 here. So we have negative 3 times positive 8 plus 33. Does that equal 5 minus 8? So we're plugging 8 into both of our x terms. Okay, so we have negative 3 times 8. That's negative 24 plus 33. Does that equal 5 minus 8, which is negative 3? That doesn't look good to me. So negative 24 plus 33 gives us positive 9. What's the square root of 9? I believe the square root of 9 is 3. Does that equal negative 3? No, it does not. So our 8 did not work. If you remember, we call that an extraneous solution. Okay. Now let's try our 1 here. Hopefully we have room. So let's plug in a 1 here. So we have negative 3. Oh, sorry, it's a negative 1. Negative 3 times negative 1 plus 33 equals 5 minus negative 1. Okay, so negative 3 times negative 1 gives us positive 3. 3 plus 33 is 36. And then 5 minus negative 1. Remember, minus a negative gives us a plus. Does the square root of 36 equal 6? Yes, it does. Okay, so the 1 or the negative 1 worked. The 8 is extraneous. So our answer to this problem is negative 1. But again, I like you guys to tell me not only the answer, but the other answer that you found that was extraneous. So x equals negative 1 is the actual official answer to this problem. but also I like to know that x equals 8 was an answer that we found that was extraneous. Okay? Okay, example 10 has two questions on it. The first one is very similar to the one that we just did, and the second one is bringing us back some fractional exponents, and we'll talk about those. So again, try these, but I'm going to do them now. So I'm going to need more room for this one, but we have this radical alone, so we can square both sides. Okay, so what we're left with here is negative 9x plus 28. Now over here, we're doing that same FOIL that we did last time. Again, maybe do some side work, or some of you might be able to do that without it. I have it done. That gives us x squared minus 16. Oh, sorry, that is not right. Let me erase that. X squared, I was getting ahead of myself here. X squared minus 8x plus 16. Okay, so we have that. Again, we want everything on one side, so we're going to move this 9x and the 28 with its friends on the other side. Okay, so that gives us 0 over here equals x squared plus 1x, or you could just put x there, minus 12. Okay, so now we're looking for two numbers that multiply to be 12, add to be 1, or sorry, multiply to be negative 12, add to be 1. And those numbers, hopefully you figured them out, are x plus 4 and x minus 3. When you solve those, when you set x plus 4 equal to 0, you get x equals negative 4. When you set this one equal to 0, you get x equals positive 3. Now we got two answers, so we're immediately suspicious. We also had the same weird stuff going on as last time. So let's check these. When we check these, we get negative 9 times negative 4 plus 28. All of that's in the radical. So we're checking the negative 4 first. Equals negative 4. Oh, sorry, negative 4 plus 4. So see how this x already had a negative. So we're saying negative 4, or the opposite of negative 4. So negative 9 times negative 4 is 36 in here, plus 28. Now negative 4 is really positive 4. So positive 4 plus another positive 4 equals 8. 36 plus 28 is 64. So does the square root of 64 equal 8? And it does. So negative 4 works. So let's try 3. So if we try 3 here, we have negative 9 times 3 plus 28. Oops, that square root does not need to extend. Okay. Equals negative 3 plus 4. So negative 9 times 3 is negative 27 plus 28 equals negative 3 plus 4, or 1. What's negative 27 plus 28? I believe that is 1. Does the square root of 1 equal 1? It does. So these answers both worked, okay? So again, you need to be suspicious when you get two answers, but that doesn't always mean that one of them is extraneous. So these were both fine. Okay, now I want to talk about this next problem. So this next problem, instead of being in a radical, has a rational exponent, or an exponent that's a fraction. So I know, again, I think I've apologized for this in a previous video, but that my exponents look large when they're fractions. But that does say 5x plus 7 to the 1/3 power. So you can think about that in a couple of ways. What we learned all through 5-6 was how to convert this into radical form. So you could think about this as 5x plus 7 in the radical, and our index, remember, power over root, so that would mean the cube root of 5x plus 7. So you can convert that first, then this just becomes just like all the problems we already did, where you would cube both sides, etc., etc. The other way you can think about this is you can use the power property of exponents. You can say, all right, if I want to get rid of an exponent that's a 1/3, so if I have 5x plus 7 to the 1/3 power, and I want to turn this into a 1 instead of a 1/3, we could raise that to the 3rd power, because 3 times 1/3 is 1. So then our exponent would kind of get canceled out also. So if you notice, if we converted it into a cube root, then we used the power of 3 to get rid of it. If we didn't convert it, we still use the power of 3 to get rid of it. So either one you want to do is fine. So you could convert it into a radical form first, so you could really maybe visually see it better. Or you could think about it as just raising it to a reciprocal power. So if you have something to the 1/3 power and you want to get rid of it, you raise it to the 3rd power. If it's the 1/2 power, you raise it to the 2nd power, etc., etc. Okay, so that being said, these are now just like all the other problems that we've done. So if you want to convert this, and it's your choice. You can convert it, or you can just raise it to the 3rd power right off the bat. So you can convert that to the cube root of 5x plus 7, then raise that to the 3rd. Then you have to raise that 3 to the 3rd too. Make sure you remember to raise that right side also. Okay, so then we have, this just becomes 5x plus 7. Oh, I almost wrote 9. This is 27 here. 3 to the 3rd power, or 3 times 3 times 3 is 27. Then we subtract 7 from both sides. We get 5x equals 20 divided by 5, and x equals 4. And that is your answer. So again, this looked a little weird because it had a fractional exponent, but you treat it the exact same way as a radical, because we know fractional exponents are just another way to write a radical. Okay, so -4 and 3 were our answers over there, and then x equals 4 was our answer here. Okay, we're almost done. We only have a few left. Okay, so here, I think if I'm looking ahead correctly, I think this is our hardest one we have left, and then we're good to go. So again, we have a 1/2 power here. So again, you could put it in radical form if you want, but I know that to get rid of a 1/2 power, I'm just going to raise it to the 2nd power. But again, if I do that on the right side, I have to do it to the left side as well. And I have to make sure everything gets raised to the power. So over here we have 2 squared, which is 4, and then x squared, which is x squared, equals, and then again, these cancel, so we're just left with 4x plus 8. Okay, now this is a quadratic, so we want to make sure that we get everything onto one side. So we're going to say minus 4x minus 8, because our 4x squared is positive, so we want to leave it. Okay, that leaves us with 4x squared minus 4x minus 8 equals 0. Now, we're going to have to factor this. Now, if you're factoring this, our first move when we're factoring, hopefully you remember, is always to look for a greatest common factor. Now, the greatest common factor here is 4. Now that we're dealing with an equation instead of just an expression, we can actually just go through and divide everything by 4. We don't have to leave the 4 like chilling on the outside. Remember, in the past, we might have done something, like this up here. With an expression, when you're factoring an expression, you have to do that. But when you have an equation, you're allowed to divide everything, because as long as you do it to one side and the other side, you're good to go. When you just have an expression, there's no other side to do it to, so you have to leave the 4 there. But now we can say, okay, so 4x squared divided by 4 is just x squared. Negative 4x divided by 4 is negative x. And negative 8 divided by 4 is negative 2. And that equals 0. Okay. So now we're trying to find two numbers that multiply to be negative 2, add to be negative 1. Those numbers are x minus 2, x plus 1. Okay, when we set those equal to 0, we get x equals positive 2 and x equals negative 1. Okay, so we're here. Now, what we have to do here is check these, okay? So these are definitely ones we have to check because we have an even power. I'm going to use this top margin. Hopefully you guys gave yourself a little more space. I have this done in a notebook and I gave myself plenty of space. Just don't have it here. Okay, so I'm going to do it up top in the margin. So we're going to plug in 2 here. So we're going to have 2 times 2 equals 4 times 2 plus 8. All of that raised to the 1/2 power. Okay. So sorry, that's kind of small. So we got 4 on the left side, and 4 times 2 is 8 plus 8 raised to the 1/2 power. So we get 16 to the 1/2 power. Now, if you remember what the 1/2 power means, that's the same thing as saying the square root. So does the square root of 16 equal 4? Yes, it does. So x equals 2 works. Let's see if x equals -1 works. So we have 2 times -1 equals 4 times -1 plus 8. All of that raised to the 1/2 power. So on the left side, we have -2. On the right side, we're going to have 4 times -1. That's 4, or sorry, -4 plus 8 is 4 to the 1/2. Now, 4 to the 1/2, again, is the square root of 4. Does 2 equal -2? No, it does not. So this -1 is extraneous. Now, the reason why that happened is at the very beginning of our problem, the first thing we did was square everything. So, again, when you square everything, it becomes positive, but when we plug it back into our original, this -1 is negative. We got rid of that problem by squaring it, but unfortunately, it's still a problem when we check and plug it back in. So our answer is x equals 2, and then x equals -1 is extraneous. So this one's extraneous, and the 2 worked. Okay. Now, this next one, again, we have a 1/3 power here. So again, you can translate that into radical form as a cube root, or you can just start right away, which I prefer personally because it's less writing, but whatever works for you. I prefer just raising that to the 3rd power right away, raising that to the 3rd power again. 1/3 times 3, when you multiply those, you just get the 1st power. So x plus 5 to the 1st power is 3 to the 3rd power, which is 27. Then we're subtracting from both sides. X equals 22. And that does work. Again, this is an odd power. Everything was good. You don't have to worry as much, but I did check it. It does work. If you want to check it for your own peace of mind, you may. But when it's an odd power, you don't have to worry as much. Okay? Oh no, we did have another annoying one. It's here. Okay, we have one more annoying one, then one more easy one, and then we're done. Okay, so example 12, we got an even power, and we have x terms on both sides. So again, that's going to make it a little bit annoying. Okay, so we're going to raise these both to the 2nd power. So we get 2x plus 15, again, those are gone, equals x squared. So let's get everything on the side with the x squared. So we're going to subtract 2x and subtract 15. Okay, so we get 0 equals x squared minus 2x minus 15. Okay, when we factor that, we are going to get 0 equals x minus 5, x plus 3. When we set those factors equal to 0, we're going to get x equals 5 and x equals -3. Now, hopefully, we've been factoring for long enough that that's not very annoying. I think, honestly, on these, the most annoying part is the plugging back in. So we have these two answers. Let's see if they're both correct. So first, let's plug in 5. So 2 times 5 plus 15 to the 1/2 power equals 5. So we're putting 5 in for both of our x's. So we get 10 plus 15 to the 1/2 power. Does that equal 5? So let's see, 10 plus 15 is 25 to the 1/2 equals 5. Remember, the 1/2 power means the square root. So does the square root of 25 equal 5? Yes. Great. Now, you might be noticing a trend here that some of our negative stuff is not working out. So I'm a little suspicious about this -3. So let's see, 2 times -3 plus 15 to the 1/2 power equals -3. Again, I don't feel great about that. Not thinking it's going to work. But let's see. We got -6 plus 15 to the 1/2. Does that equal -3? This is 9 to the 1/2. I believe 9 to the 1/2 is just 3, not -3. So that does not work. Okay, so again, our answer, I keep writing right where my answer is popping up. One day I'll get better at that. So our answer is x equals 5, and the x equals -3 is extraneous. Oops, I did not mean to erase that, but I'll write it back. Okay, so x equals -3 ended up not working. X equals 5 worked. Okay, it's our last problem, and I don't think it's that bad. So last one here. Okay, now, I know there's one like this on the test, okay? And it's, everyone, gets confident. They're like, oh, it's a pretty easy one. And then they forget the first step, okay? Now, we haven't seen one in a while where a radical wasn't alone. So again, I know this is not a radical term, but it's a rational exponent term, which is basically a radical. This needs to be alone. Now, you could do this problem if this wasn't alone, but you can't always, so I don't want you to build bad habits. That's your radical term right there. So we need to first do what? I want you to think about what we would do here to get that alone. All right, so what we're going to do here first is divide both sides by 3. Then that leaves, so we're left with x plus 6 to the 1/2 power equals 9 divided by 3, which is 3. Okay, now to get rid of our 1/2 exponent, we square both sides. So we get x plus 6. Oops, I didn't square both sides. Make sure you square both sides. Again, all of us make those mistakes sometimes. 3 squared is 9. Okay, then we subtract 6 from both sides, and we get x equals 3. And again, you can check that. I'm going to do a mental check on this one. So I'm going to say 3 plus 6. Okay, that's 9. 9 to the 1/2 power, or square root of 9. That's 3. 3 times 3 is 9. Okay, but yeah, you can write that, check out. This is 3. This is the end of our lesson. This is the end of our unit. The test is approaching. Make sure you look out for information about that. Okay, make sure you ask questions. Make sure you do your homework. And more importantly, not more importantly, but just as importantly, make sure you see this video, these dogs eating peanut butter and jelly sandwiches. But if you have any questions, please make sure to contact me. And that is all.